Hi there, how you doing? This is our video report for the paper, which is Quantum Algorithm for Linear Systems of Equations. I'm a senior, and my name is Komorkat.
I'm also a senior. My name is Vasil Bhargava.
And my name is Josh Prunny, and I'm a junior. All right. So the paper we chose is about a quantum algorithm for estimating weights in a system of linear equations. So as opposed to a classical computer handling a similar issue, which would scale at least linearly with the number of equations in the system, the approach described in this paper can scale logarithmically with the system size. And additionally, it'll scale polynomially with the condition number and the required precision. So setting up the linear system for this algorithm, we have AX equals B. In this case, A is a known sparse Hermitian matrix, and B is a given vector, where our goal is to find X, the weight vector for the linear system. So initially, the quantum algorithm will encode B as a quantum state, and then utilize quantum phase estimation and Hamiltonian simulation to perform the matrix inversion. And what this will yield is a quantum state representing the solution X.
All right, yeah, so we're just going to talk a little bit more about the algorithm. If you want a more detailed report, you can go look at our write-up. But the first thing we're going to do is we're going to convert A to a Hermitian matrix if it is not so already, so we can work here with quantum algorithms. Then we're going to prepare B and decompose it into the eigenbasis of A using phase estimation. Next, we're going to apply conditional Hamiltonian evolution and perform a quantum Fourier transform. Then we're going to introduce a new qubit to the system, apply controlled rotation, and invert the system. And lastly, we're going to take a measurement on the last qubit of the system to collapse the state to the solution and get the information about X using a measurement on M.
So now to get into the runtime and error analysis of the algorithm. The algorithm's performance is sensitive to the condition number kappa. Kappa is a value which is given by A, which is the ratio of the largest eigenvalue to its smallest eigenvalue. And a larger kappa reduces the stability of our solution because as its value increases, the ability to invert A also decreases. And phase estimation introduces the main error in this algorithm. It's proportional to 1 over t sub 0 when estimating our eigenvalues represented by lambda. And t sub 0 in this is a time parameter that optimizes the phase estimation. And an eigenvalue of lambda with lambda greater than or equal to 1 over k sets this t sub 0 parameter to kappa over the error, which in turn influences the final error. And overall, the runtime of this algorithm is O of log n times s squared times kappa squared divided by epsilon, where n is the size of the matrix, s is the sparsity of our matrix A, and kappa is a condition number, and error is the epsilon. Error is represented by epsilon, as mentioned earlier.
All right, so we'll get into sort of the closing discussion of the paper here. The authors suggest some possible extensions of the algorithm for a broader class of matrices, and that's going to include non-sparse matrices and non-Hermitian matrices. And then we discuss some challenges with the algorithm. In particular, one big issue is the scaling of kappa. So if the condition number kappa scales exponentially with the matrix size, then the quantum algorithm might not offer an advantage here over classical algorithms. However, if kappa is polynomial or polylogarithmic, then the quantum approach can be more effective. Some techniques are discussed to handle large kappa values, and that includes focusing on well-conditioned subspace of A and applying preconditioners. And finally, the authors close with some discussion of generalizing outputs of this algorithm that might be able to be used to estimate higher degree polynomials. And there's some final discussion about performing quantum Monte Carlo calculations as well.
Thank you so much for our presentation.